Alright, what's going on, guys? So today I want to go over some more. This is more in quantum mechanics, and again, if you're new to this channel, I'm certainly new to this as well. I've decided I wanted to take on this project of teaching you guys advanced science, partly because I am entrenched in advanced science, and I really love thinking about this kind of stuff and doing this kind of stuff. And so I'm paralleling this book here, Modern Quantum Mechanics by Sakurai, and so today I want to go over sort of a little bit of the importance of I, but more on practical observables and operators and eigenvalues and all that kind of stuff. And I'm going to try to start again from basic principles, and I'm going to work up from there. And so, without me talking too much about an introduction, let's get right into this. So I want to go back to Calculus 2. If you remember from Calculus 2, we can recall that the sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, and then we just alternate pluses and minuses, and you can see the pattern here. We have odd numbers in the exponentials and odd numbers in the denominators. They're the same there, right? So that's the sine of x. This is the Taylor series expansion of the sine of x, and basically what the Taylor series does, or what it is, it's a rewriting of a trig function into an arithmetical function, a function that has just pluses and minuses in it. Okay, and the more we sort of go out on this Taylor series, the better the estimate we can get for the sine function. Okay. And so let's take a look at the cosine function. So the cosine function is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus, and so on. Again, this is it for the cosine, right? And the only difference here is that we're working with even functions, or even values in the exponential and in the denominators, and they're the same there. Right, so the last one here I want to look at is e to the x. Okay, so e to the x is 1 plus x plus x squared over x factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus, and so on. Okay, so this is all from Calculus 1. So Calc 1, or actually Calc 2, I think, is where you learn this kind of stuff, in series and all that kind of stuff, and where you learn about Taylor series of, so these are Taylor series of sinusoids. These are sinusoidal functions, sine and cosine. These are they're oscillatory functions. You can think of them as that as well. So they oscillate. They go up and down through space and time. Okay, these ones are just particularly in space because x usually denotes space. If we were to just replace it with t, then we're talking about a function that oscillates in time, right? And e to the x is something that blows up, that gets that blows up in space. Think of something that gets really large really quick, and you can model that with an exponential. It doesn't even have to get really large really quick. We can divide x by 2, or we can multiply it by 2, and we can change the rate at which the exponential actually increases, right? So these are the basic sort of building blocks of how we model differential equations as well. Okay, and when we go through numerical analysis, I'm going to go through that. I'm going to go through that too, but that deserves its own playlist. But what I'm interested in now is looking at what e to the ix might be. Now the motivation for this is a little bit unclear, right? The I is a complex number, and complex analysis wasn't sort of discovered until later on in the game, or later on in history. But when I was established as a relevant sort of phenomenon in math, people started to play around with it, and Euler was one of those guys that did that. I think he was alive during the 1800s. I wouldn't really quote myself on that though. He's a very, very intellectual mathematician, very smart guy. I believe he was blind in one of his eyes. I can't really remember exactly what the deal with that was, but again, nevertheless, he was very, very smart. Leonhard Euler, I think was his name. And what does this equal? So wherever we have an x here, we just want to put in I to the x. So we have 1 plus I to the x plus I to the x squared over 2 factorial plus I to the x cubed over 3 factorial plus I to the x to the 4 factorial. Okay. And so what does this equal? So we know a little bit about I. I is the square root of a -1. Okay. And so this equals I, so 1 plus I to ix, all right, and then plus, so I squared is just -1, so this is actually negative, so minus x squared over 2 factorial. And again, that comes from I times I. So this I here is squared. I times I is -1. That makes this a negative. Okay. And so then I times I times I, so it's -1 times I, so that's negative I. Negative I x cubed over 3 factorial. Okay. And then so I times I is -1, and I times I is -1, so -1 times -1 is going to be +1. That's x to the 4th. And that's going to be 4 factorial. And then I'll do it again to the 5th. So I times I is -1, I times I is -1, so that's positive. And then we get a positive I by multiplying that by another I. So we get positive x to the 5th. I x to the 5th over 5, like that. So we have these alternating i's. We have i's here, and i's here. But we have a minus, minus, plus, plus, and we'll see that pattern as well too. So the next one's going to be minus, and it's just going to keep on going. Okay? So let's take a look. I'm going to use a little bit of color here. So we have x, we have this guy, and this guy. That's right there, and right there, and then I actually don't have an x to the 7th out here, but you kind of start seeing the pattern. Wherever we have these guys, we have i's in front of them. So if we just multiply this whole thing by I, so I sine x, right? I sine x is I times x, I times this, I times this, and I times this, and we get exactly these terms in here. Then we can add that to this, and we get exactly this. We can add that to the cosine of x, and we get exactly this, such that we get this relationship, e to the ix, e to the ix is equal to the cosine of x plus this I sine of x. Okay. Now this here, I'm going to actually bold box this a little bit. this here is very important formula. And why? So you might think, okay, why in the world is this important? Well, it's important because we're relating exponentials with sinusoids. So we have a relationship now. But not only that, we can say that if we have an I in an exponential, right, and this e to the whatever, if we have this I here, that means we're looking at a sinusoidal function. We're not looking at an exponential function. So the I sort of transformed, putting an I in the exponential, sort of, again, you can say it kind of operated on the exponential to transform it into a sinusoidal function. So we went from something that looks like this, so an exponential looks like this, so that might be e to the x, right? And we went to something that looks like this. This is e to the I x. Okay? It's just got this imaginary part to it too. So in some sense, it's more of a canonical transformation, if you will. We don't just get real parts of a function, but we get the imaginary part of the function as well when we place this I in the exponential. So when we place an I in the exponential, we're transforming from exponential to sinusoid, and that's good. It's very important, especially when we want to be able to read quantum mechanical equations, specifically in something like quantum field theory, because in quantum field theory, and even in advanced quantum mechanics, you'll find stuff that looks like this. So we might have, so as an example, we might have something that looks like e to the I, and then an integral, for example, negative infinity to infinity of h of t dt or something like that. So, okay, this argument is here. So we have this integral of something, but we have this I here. And what this I is telling us is that this whole thing is a sinusoidal function with respect to this as sort of being the independent variable. So this integral is sort of the independent variable, much like x was the independent variable here. And so that's how we can begin to read stuff like this. So when we get interested in quantum field theory, and when I start that playlist, I'll allude to this kind of stuff, and I'll say this is a sinusoidal function because we have this I right here, and yeah, so that is the importance of I in quantum mechanics. That is one of the most important aspects of the number I in quantum mechanics. Okay, so what I want to do now is, I wonder if I have enough space on this slide. I think I do. Actually, no, I don't think I do. So I will move on to another slide here to illustrate the next point that I want to go over. So this next point that I want to go over is something that Leonard Susskind talks about in one of his lectures. I think he was talking about it in his lecture on quantum mechanics. I think it was like his first or third lecture on quantum mechanics on YouTube. And what we have is, let's consider we have f of x is equal to e to the alpha x. Okay, now alpha could be imaginary, it doesn't have to be imaginary. But let's think now. So we have f of x. So if we want to find f prime of x, we know what the derivative of this is something that you go over in calculus 1, alpha e to the alpha x. So we can actually write f prime of x as alpha f of x. Okay? F prime of x is the same thing as dx of f of x equals alpha f of x. Okay? Let's just take out, so since we have f of x here, f of x here, so what we're saying here is that d dx is equal to alpha, right? We could sort of divide out f of x if we can do that, but it doesn't. It makes mathematical sense to do that. It's just not something that we typically do. But what this enables us to see is that merely multiplying an exponential by this constant here, whatever we have here in front of our argument, whatever we have here in front of the argument, we have but merely by multiplying the entire function by that, we can get some information on what the derivative is like, okay? On what this derivative is like. So we don't have to go through the complications of actually taking the derivative of maybe some complex function. We can merely just multiply it by this number here, complex or not complex, right? And this is an eigenvalue problem. And what we say here is that this is the operator, right? So if we have some operator, d dx, right? And all this operator does is multiply some function. We don't really know what this function is. It's a specific function. We don't really know what it is, but this is the operator. This is the operator's corresponding eigenfunction, right? And this is the operator's corresponding eigenvalue for that eigenfunction, okay? And so the operator, it doesn't just operate on every function such that this is the case, okay? It doesn't operate on every function such that this is the case. And what that enables to sort of for us to sort of visualize in our head a little bit is, okay, we have an operator and we have a set of functions. Again, functions can be defined as vectors, like I talked about in my first lecture on this stuff. So if we have some operator, it has its associated eigenfunctions or eigenvectors, okay? So say we have some operator, so now I'm just talking in general terms. So generally speaking, if we have some operator O, automatically we can figure out it has some eigenfunctions, it has some eigenvectors, so it has its own set of eigenfunctions, and it has its own set of eigenvalues. So the eigenfunctions are f of x and the eigenvalues are alpha. So all we need to know is what the operator is, and then we can discern everything else. Okay? This is the power of eigenvalue problems. And this comes up a lot in quantum mechanics. Okay? So let's take, for example, now d dx of some function cosine of kx. That looks like a bad x. Kx plus I sine of kx, where k is just some number, okay? We'll understand a little bit later exactly what k will actually mean for us in quantum mechanics, but let's just figure out what this is. So this is what this is so the derivative of cosine of kx is negative k sine of kx. If you remember this from calculus, we're basically doing chain rule here. And then plus ik. So we have this I, we're multiplying it by the constant of, not sine, this is cosine kx. Okay. And so what we can do now is if we take out ik, and what that leaves us with, cosine kx plus I sine kx, like that. Okay, so we have, again, so we can multiply this too. We get, if we multiply this by this, we get this here. If we multiply this by this, we get this here, right? And cosine kx, I sine kx, that's the same thing as this. So that's the same thing as I k f of x, right? Because this sort of follows this pattern of f of x. So I'll just say f of x, where f of x is this. So this here is f of x. Okay, so what does that tell us? That tells us that k is an eigenvalue for this operator. Okay? It's an eigenvalue for this operator, so we could say that dx is equal to ik. So if we multiply our sinusoidal function, or our oscillating function, by k, this little element in the argument, we multiply the whole thing by k, we can get some idea on what the derivative, we can get some information on what the derivative is like. Okay, so k here is an eigenvalue for this operator applied to this function. Okay. So similarly, say we have omega t, right, and we're doing this whole process again, but instead of kx we have omega t. We can do the same thing, and we can figure out, we can see that I will actually I'll actually move to another slide here, so we can actually figure out, and we could see that if we have a wave, so e to the I right there, that's a wave, okay, and here's our argument, kx plus omega t. And I can let you go through this, it's not that hard. So that equals the cosine, of kx plus omega t plus I sine kx plus omega t. Right, so this here is a wave. This here's a wave, and it takes this form. We can, and what we'll see if we do the derivative of this with respect to x, we'll basically find out that, again, this is just ik, because this is all linear. This is all linear. So you can take the derivative of this, and you can find that the eigenvalue for dx is ik, and the eigenvalue for dt is I omega. Where k is associated, k is the eigenvalue associated with the derivative with respect to position. Okay, so that's a velocity. Or not a velocity, I'll just keep it at that. I'll just say k is the eigenvalue associated with the derivative with respect to position. And omega here, this w, is the eigenvalue associated with the derivative with respect to time. These two things are operators. These two things are eigenvalues. All right. So again, I can't stress this enough. And since I'm not on a limited time here, and I can make as many videos as I want, I will repeat this throughout. I will repeat this throughout the lecture series, just to stress the point that that multiplying by k of these waves is is equivalent to taking a derivative. Okay, and we all know multiplying by some number is much easier oftentimes than taking a full-on derivative. Okay, and so I want to get into now the Schrödinger equation. Now that we have all this behind our backs, I want to get into the Schrödinger equation and look at it a little bit more in depth. Okay, so we want to recall now some basic fundamental principles about wave mechanics. So in wave mechanics, recall that k is the wave number. K is a wave number, and it's equal to 2 pi over lambda. And omega is the angular frequency, and that's 2 pi times the frequency. Okay, so k, automatically we could see that, okay, for this wave, for any wave here, the k, this eigenvalue, is associated with the wavelength of that wave. So the wavelength is also an eigenvalue for ddx. Okay. Likewise, the frequency of the wave is an eigenvalue for ddt. Okay. But we also want to recall that the momentum p is equal to hk, and the energy is equal, the total energy of a system is equal to h times omega. So see, these are some very important concepts here, right? And I'm not going to go into them in depth because that's just going to make this video way too long, and I'm assuming you know this already. Because again, I'm aiming here to go for advanced stuff, but again, there's just some stuff in here that I feel I really just can't pass up. Some of the basics I just really can't pass up. So I'm establishing many of these earlier videos to sort of reintroduce you to this kind of stuff, so that we can recall this for more advanced study. Okay, so these are the k relationships, how k is related to p, and how k is related to the wavelength, and here's how omega is related to the frequency and how energy is related to omega. Okay. So this is a total energy too. This is the total energy of some particle or some system. Okay. And so let's take this here. If we can multiply, what we'll find is we could take the double derivative of this, or we could just multiply this, or we could just take the square of this. We can just take the square of this, and we find that dx, so d squared dx, so taking the double derivative is the same thing as I squared. So I squared is just -1, so negative k, that's a bad looking k, so negative k squared. Okay, and so, and then ddt I'll just rewrite down here. We're not going to be particularly interested in doing anything with ddt, so I'll just keep that as I omega. Okay, so that's just a copy of this down here. So k squared, okay, so k squared is p squared over h squared. Okay? So k squared is p squared over h squared. So that's negative p squared over h squared. So dx squared is just p squared over h squared. Okay? If we multiply both sides by h, we can get h h squared dx is equal to negative p squared, like this. And we can do this here, ddt is if we multiply both sides, we can multiply both sides by I, or divide both sides by I. I'll do that. So if we divide both sides by I, and then we can, I'll just go like this. So 1 over I is equal to omega, and omega is E over H. So that's equal to E over H. And this is a total energy, so E total. This is the total energy. E over H. Actually, I will make that H look a little bit better. E total over H. Okay? So what we will find here is that if we divide both sides by 2m, we divide both sides by 2m, this here is a kinetic energy. Okay, so the kinetic energy, therefore, is the eigenvalue for this operator here. So if we can somehow measure the kinetic energy of a particle, then we understand what taking its double derivative is like. We can get some information on what its double derivative is like, and then all we'd have to do is compensate for these constants out here. If we know what the mass of the particle is and Planck's constant, then we can get some information again on what that's like. Okay, and similarly, this is the total energy here. So what we have here is H over I ddt is equal to the total energy. Okay, and so we know that E total is equal to kinetic energy plus potential energy. Okay, well, this is the kinetic energy, so that's just equal to h squared over 2m dx squared. I'll put a line right here too, just something. This is something that we have to recall. And then we have this P, this potential energy, and we'll call that V of x. Okay, we'll just have this be one-dimensional for right now. Okay, and so ET here, the total energy is this operator. So like that, we have d dt. Okay, so this is basically the Schrödinger equation. Okay, d dt has to act on something, this has to act on something, and this has to act on something. So these are all operators, right? So what we have here is h over I d dt of phi of, this has to be a function of x and t, okay, is equal to h over 2m squared d dx squared phi of x and t plus v of x times phi of x and t. Right, so this here is the Schrödinger equation. So Schrödinger equation, time-dependent Schrödinger equation, okay, because we have this element of time in here. Okay, so the derivative with respect to time of some function, and again, this function is a state, right? And that state can be represented as a ket vector, and it has its corresponding bra vector as well. If we multiply that, or if we operate on that by this, we can get some information on what this whole thing is like. Or if we operate on another way, we can write this. I don't know why I put an h bar right there. You can put an h bar right there, and we will, but I'm really just looking at basics right now without actually doing too much multiplication and stuff like that. dt, right? We can say that this is the same thing as if we just assume now that this here is a function of x and t, is h squared over 2m d second derivative plus v of x. Okay, all of this is an operator basically and acts on psi. So all of this is an operator and acts on psi, and all of this is an operator. This is the same thing as this is another way we can look at the Schrödinger equation. Okay, and so yeah, so this is the Schrödinger equation, and we've developed the Schrödinger equation. We've developed the time-dependent Schrödinger equation. There is a time-independent Schrödinger equation. That's just that the time-independent Schrödinger equation is basically we omit this part here. Okay, we're not really interested in how the equation changes with respect to time, but since this is an advanced course, we are going to be very interested in how this changes with respect to time, how this function changes with respect to time. Okay, so we have the time-dependent Schrödinger equation. I just want to talk about a few more things before I leave you to think about this kind of stuff. And the first is that we have, okay, so we have the time, so now we've developed the Schrödinger equation, and we understand that k and omega are eigenvalues of dx and dt respectively. Okay, so k and w are eigenvalues of ddx and ddt respectively. And so one of the things I want to really tackle in throughout this whole channel is the idea of being able to read equations. Okay, because oftentimes we're presented with equations in textbooks, and we don't really. We're kind of just shown the equation. We're like, this is the case, okay? And it's hard for us to make sense of it. And I've read a lot of books. I've read a lot of physics books in my day, and I don't think that's a very good way of going about understanding physics, because first of all, it takes a lot of time to actually be able to understand this kind of stuff, let alone having to decipher it as if it's like some new language to us. And so let's take a look at this here. How can we make sense of something that looks like this? Kx plus omega t. Okay. And then we want to integrate this over k. This is something we're going to find a lot in quantum field theory, but it's also helpful to understand this in advanced quantum mechanics. So we integrate this over k, and we're going from, I don't know, say k equals 1 to k equals 4 or something like that. All right, so what is it? So how can we make sense of this? So this is a sinusoidal function, okay? But we're treating it as if the independent variable was k and not x or not t, okay? And k, again, if you remember, is the eigenvalue associated with the derivative with respect to position. So we only have a certain set of k values, okay, because our operator is very specific in that way. There's only a specific set of functions that DDX can act upon to give us these values of k, right? And those specific set of functions are sinusoidal functions. So this is the sinusoidal function, and we are integrating again over k. Now nothing here in this kernel or whatever you want to call it is squared or anything like that. So we can think of this as a graph that looks like this. It's a sinusoidal function. Sinusoidal function and this is e to the I kx plus omega t, okay? But instead of this axis being x, this axis is k. Okay, so we have this eigenvalue, this eigenvalue, this is an eigenvalue point, this is an eigenvalue, that's an eigenvalue, this is an eigenvalue, this is an eigenvalue. And we can keep on going. So these are each, since this is quantum mechanics, this is actually quantized. There's only specific values of k we can have. Specific values of omega as well that we can have. But basically what we're doing here is we're saying k is the independent variable, okay? K is the independent variable in which we can choose one of these variables and we get the value for this wave right here. So say we choose, so this one here would be, so say we choose this one. So this would be K1, K2, K3, K4, so K5. So right here is K sub 5. So this is our fifth eigenvalue from 0. Okay. This is our fifth eigenvalue from 0. And that corresponds to this value here. And if we're integrating, actually, we want to go to 4 actually, so I'll actually make this a little bit better. So we have this here is K4, so K4, and this here this here should, you kind of get the point. We want to go from K n where n equals 1 to K n where n equals 4. So where n equals 4, where n equals 1. Okay, so so here's K equals 1, here's K equals 4, or n equals 4, and we're doing that integration right there. Okay. Now, I also want to talk a little bit about a more general form. Okay, a more general form of this. So, as I went over here, we have e to the I kx omega t. That's this. Okay, so what if we had e to the I kx plus omega t? All right, and then we also had plus e to the negative I kx plus omega t. How can we read that? And what if we wanted to integrate that over d omega? Okay, so this is like one example, and here's another example, and we wanted to integrate that over omega. Okay, and so that means our x-axis is this guy here. That means our independent variable is omega, and we're integrating over all of the possible eigenvalues that are associated with d dt on this wave. Okay. And without alluding to too much and getting going too far off the beaten path, I do want to make mention a little bit of something we call creation and annihilation operators. Okay, I'm not going to go into their detail right now. I'm already pushing almost about 50 minutes here. And I don't want these lectures to go on for too long. But we can say that we have these things here called creation and annihilation operators. And I think these here tend to be called creation operators, and these things here tend to be called annihilation operators. And we actually have to put subscripts on these k's, because again, the k's here, they're quantized. This is quantum mechanics. They're quantized. These are the specific eigenvalues that are associated with taking derivatives of certain equations. And so these are taking time derivatives of these sinusoidal equations. And so these are creation and annihilation operators, and these things are, you can see their functions. And oftentimes what we'll find in quantum field theory and also in quantum mechanics is this idea that the weights on each wave here, so this is a wave, okay? This is a wave, the weights, once we put weights on this thing, we are looking at it's almost a completely different beast here. So we could say that k and e to the I k x plus omega t. Okay, and we want to, if we say we want to integrate over k, and we're going from k, and say there's a subscript on the n here, n equals 1. This is just another notation. Okay, we're not integrating. We're not really finding any. We're not really finding an area per se with this notation here, but say we wanted to go to 3, n equals 3 here. We're adding here. This is a Fourier transform. Okay, and I haven't really gone over Fourier transforms, but what we basically have going on here, okay, this took me a while to realize, is this is a series of waves, and each wave has a different value for k, okay? And what this is basically telling us is that, okay, if we know that k is some sort of proxy for momentum, then what that basically is telling us is, okay, we have some particles that are at some momentum, okay? So say these black particles here have a momentum, have momentum values of k1, okay? And they're moving like that, and then we have, say, some particles here, the green ones, here they're moving at some momentum of k2, and then say we have some particles here, they're moving at some momentum k3, okay, and say we have a lot of red ones. So we have not a lot of black ones, not a lot of green ones, and we have a lot of red ones. So we can actually kind of begin to make sense of something like this. Okay. This here is a function. Okay, this is a function that acts on k. So, and what this is basically telling us is the weight here. This becomes a complex function because we're summing over multiple sinusoidal functions. And when we sum over multiple sinusoidal functions, what you get is you can begin to understand what a Fourier transform is like. Say we have a wave. This is like the overall wave looks like this. Okay, this is, and it's along some axis here. Okay. And this weight that we have up here corresponds to the weight of each basic sinusoid, that is contained within this complex wave. And this is what Fourier transforms do. So say here, I sort of used a bad color here. I'll go over this in blue. So say these guys are blue, and they're going at a value of k1. So say this is what that wave looks like. Okay, and then we have say this is what I'm not doing this very well, but this is what the red one looks like, and then I need to put the green one in here too. And just let's say this is what the green one looks like, something like that. The number of particles at a given momentum corresponds to the weight that we place on, or the importance that we place on one of these building up waves, one of these waves that build us up to the overall wave. All right, so we have an overall wave, and it can be broken down into its various components. Okay, and each component, the degree to which each component contributes to the overall wave, that degree corresponds to how many particles are moving at the momentum for that component of the overall wave. I hope that was easy to, I'm trying to break this down as best as I can. But basically, the number of particles that are sort of, you could say, indistinguishable, the number of particles that are moving at a particular momentum correspond to a traveling wave, a basic traveling wave, and if you have a bunch of different particles moving at different momenta, okay, we're basically saying, okay, the ones that are moving at this momentum have this wave. The ones that are moving at this momentum are moving according to a different wave. We add all those waves up, and we get an overall wave. Okay, and the degree to which we add one to all of them depends on how much particles live sort of within that wave there. Okay, and so I tend to think about this in terms of components. You have an overall sort of wave function, okay, It's complex. It looks great. It might look crazy, okay? But it has essential components to it. And that is a key concept in quantum mechanics that pervades everywhere. You'll see this everywhere, okay? And we can really, really actually be able to make sense of this kind of stuff. We can really be able, and not just in quantum mechanics as well. You can sort of think of atoms as the same way. That's the same thing. I'm sitting here at a wooden table, okay? The wooden table consists of multiple atoms, okay? Multiple different types of atoms, okay? And the atoms, say the table's mostly carbon atoms, okay? So those carbon atoms contribute, therefore, the most to the table, okay? And then say there's a little bit of nitrogen atoms in the table, okay? Those contribute to another component of the table, right? But that component doesn't, it's not as profound as the carbon component of the table, okay? Another example in physiology, for example, if you're interested in physiology, that is what you do when you're taking an EKG. You're figuring out what the components are of a complex thing it repeats itself. It's a sinusoidal function. It repeats itself. It's complex, though. It's flat in areas. It spikes in some other areas, right? But it has its basic components to it. And you can discover what those basic components are by basically measuring the beat of the heart at different locations along the body. Okay, that's why they put all those patches on you. They're trying to figure out what exactly those components are. Okay, and then you can actually get some information out of that. This is basically the same thing in quantum mechanics and in quantum field theory. We're looking at the components of something. Okay. And so without further ado, I'm pushing an hour here, but this is one of the more profound, I think, lectures that sort of came to my mind as I really started thinking about this kind of stuff, and it sort of came to me. This was like an aha moment for me a while ago, and it was very exciting to sort of come to this realization and sort of validate it, and being able to actually, this is a propel forward in being able to actually read quantum mechanical equations. And so without further ado, I hope this was very, very helpful to you. Again, this channel is in its infancy. I started this channel I think less than a week ago, and this is a very sort of lackluster way of doing things. But again, my aim here is to just give you the information, right? Give you the information straight up, so that you can do with this what you will. And again, I do plan on creating a Patreon page, but I just want to get more videos out there before I do that. And your contributions are going to help in me being able to take in more information, think about the information in ways that is easy to teach and easy for you to understand as well. And again, I'm not just sticking to quantum mechanics. I'm going to be making other playlists in the future on physiology, on quantum field theory, on classical mechanics, and again, each playlist is going to parallel a book, about approximately speaking, if there is a book to be followed. If there's not a book to be followed, then the playlist is going to go the way I want it to go. But again, this is aimed towards teaching you the most basic information that you could possibly attain, and be able to use that basic information to understand advanced stuff as well. And that's the main purpose of this channel, is for you to basically be able to understand advanced topics using basic principles. And thanks for watching.